We are now in section 2.4. The monotone convergence theorem and a first look at infinite series. We already know that the convergence sequences are bounded, and well, I mean, you had already discussion on Tuesday, which asked you whether the converse is true or not. In fact, it's not very hard to produce an example of bounded sequence that does not converge. I mean, just think of an oscillating function. And okay, so I mean, you'll probably see more of that on Thursday for the mock exam. Now, the point here is that we don't have that many, tools. So we have the definition of convergence, which allows us to prove that something, I mean, given a certain number, we can try to prove that sequence AN converges to that number, L, usually denoted, the limit is usually denoted by L for a limit. But we cannot, otherwise, I mean, if we have not identified the limit, we cannot probably try to prove by hand that there's a limit to a given sequence, just knowing properties from the sequence. There are only few theorems, few ways to guarantee that a sequence will be convergent. And one way to do so, one first the result that addresses this is in a particular case, in a particular kind of sequence, sequences that are monotone. So one first result that allows us to say that a given sequence converges is the monotone convergence theorem. And for that, I mean, we need to introduce the notion of monotone sequence. So I'm gonna use a slightly different notation here from the book. So I'm gonna say AN is non-decreasing if A sub n is less than or equal to A sub n plus 1 for all n in n. So the idea here is that non-decreasing non-decreasing means that the sequence never goes down. So it may go up, may not, but it never goes down. A sequence and yeah, sequence AN is called non-increasing if AN is greater than or equal to A sub n plus 1 for all n in n. And if a sequence is either non-decreasing or non-increasing, then it's called monotone. Sequence can be both at the same time. So a constant sequence, so 3, say an is equal to 3 for all values of n, is at the same time non-decreasing and non-increasing. So, but if either of those two things, can be just be monotone, non-decreasing or non-increasing, if either of those things hold, then the sequence will be called monotone. And as you said, so the idea here, that one of the tools, the first tools that we have is one of the tools that we can apply to a sequence to show that it converges when we don't actually know the limit or don't have the hope to know the limit, is the so-called monotone convergence theorem. And of course, it makes reference to this definition that we just given, definition 2.4.1. So this is what a sequence a monotone sequence is. So a sequence that either never goes down or never goes up. This is strictly increasing if or increasing if an is less than a sub n plus 1, and is strictly decreasing if an is greater than a sub n plus 1 for all n in n. And the idea behind this definition is it allows us to say something about the behavior of the sequence. So we know that on the one hand, since there are no oscillations, if this any such sequence is bounded, so for instance, if you have a non-decreasing sequence, if it's bounded from above, then you'll be able to find a limit. And the same thing holds for non-increasing sequences, and that's the relation between the two things, the two concepts. Okay, one is just a mirror of the other one. So if a sequence is non-decreasing, then minus a sub n is non-increasing, right? So just flip the signs everywhere, and vice versa as well. So really, the only important thing is the monotone quality of the sequence. And as I said, the point here in the next theorem is that even though we actually, in most applications, we will not be able to say what the limit is, so we cannot show that an converges to some given number. So you may never know what the number, this actual number is. You can say for sure that the sequence is convergent, so it converges to a limit, which you do not know. So far, we've only given examples where you actually can identify a candidate for the limit, and you actually prove by hand, then using definition, that that's the limit. So of course, if you show that this is the limit and show by definition that that is the limit, then you've shown that the sequence is convergent. But how do you show the convergence when you don't know or you don't have a candidate for the limit? An explicit candidate for the limit. Well, this is one such result. This is the first result that allows us to say that. So this is it gives you convergence without actually giving you any way of computing or finding the limit. So this is the theorem 2.4.2. Again, of course, this is monotone convergence theorem. So if a sequence is monotone and bounded, then it converges. Okay, so this is simple looking statement. And what is the idea? In fact, we reminded that the sequence being monotone means that it's either non-increasing or non-decreasing. So if it's non-decreasing, You just need it to be bounded from above, right? Because it's going to be immediately bounded from below by a 1, because all the other elements are at least equal, I mean at least as big as a1. So a1 bounds from below all the other elements. So a1 is less than or equal to a2, a2 is less than or equal to a3. So if you have that the sequence is bounded from above, then it's actually bounded and you don't need to check anything else. So for non-decreasing sequences, you just need to check that the sequence is bounded from above, and for non-increasing sequences, just need to show that it's bounded from below to apply this theorem. The thing is, here we have a non-explicit candidate for the limit. So proof, we claim, this is our claim S is equal to the supremum of the an and in n respectively the infimum, respectively S is equal to the infimum of the an such that n is in n when an is non-decreasing, respectively non-increasing. So what does this mean? This means that you take you take S to be equal to the supremum when A is non-decreasing, and in the infimum when an is non-increasing. Okay, supremum for non-decreasing and infimum for non-increasing. So we claim that S is actually the limit of the sequence. So we need to show my definition again. So we need to show, well, you all know the definition, so we need to show that given an epsilon greater than 0, right? So given an epsilon greater than 0, we can find n in n such that a sub n minus s is less than epsilon for all n greater than or equal to n, no, for all n greater than or equal to n. So that's what we need to show. Why? Because S is our claim limit here, so that's what we want to show. But then the point here is we need to find this n. And how do we do this? So we're just gonna do it in the case of a non-decreasing sequence, the other one being analogous. Is non The other case being analogous. So what is the idea? So if we're in the case where the limit is the supremum, because an is non-decreasing, so since s is equal to the supremum of the an's, right, by definition, remember that we've given ourselves an epsilon, an arbitrary epsilon. S minus epsilon is not an upper bound. If it were, remember that then S would not be the least upper bound. It's not an upper, so it's not an upper bound for the set. This is one of the characterizations that we gave for the supremum a while back. No, this is the characterization, the useful characterization we gave for the supremum a while back. So since this is not an upper bound, there exists on n, because all the elements in that set are indexed by natural numbers, such that a sub n is greater than s minus epsilon. Remember, that's what it means for this not to be an upper bound. So there's an element in the set that is bigger than s minus epsilon. Epsilon again is the same we fixed at the beginning. Okay, so an is bigger than s minus epsilon. But since a sub n is non-decreasing, we have that a sub n is greater than or equal to a sub n for all n greater than or equal to n, right? A sub n, capital N, is less than or equal to a sub n, capital N plus 1, and in turn that's less than or equal to a sub capital N plus 2, etc., until we reach a sub n. But this is greater than s minus epsilon. I mean, we knew that this was true because there must be an n in n such that this holds. Otherwise, s minus epsilon would be an upper bound for the set. Right, so we've shown that for all n greater than or equal to this capital N, a sub n is greater than s minus epsilon. But also, on the other hand, we know that a sub n is less than or equal to s, which is less than s plus epsilon. So we know this because s is an upper bound. I mean, it's the least upper bound, in particular an upper bound. In particular an upper bound. Okay, so now putting these two things together, so an is greater than s minus epsilon and is less than s plus epsilon. We then conclude that an is greater than, of course, s minus epsilon, so that means that s is less than, no, minus epsilon is less than an minus s, which is less than epsilon, by looking at this inequality here. So So an is less than s plus epsilon. So you subtract epsilon here on this side and on this side, then you get this first inequality. And if you use this inequality, s minus epsilon less than an, it's really less than an because s minus epsilon is strictly less than a sub capital N. Also, it doesn't matter this is less than or equal to. The a sub n will be greater than, strictly greater than s minus epsilon. So we can subtract s on both sides, and so here, well, sorry. So yeah, if we subtract here epsilon yeah, okay, so we subtract epsilon on both sides, we get this inequality here. S on both sides, we get an minus s is is greater than minus epsilon. So we have already shown this, so this is what confused me here. We are showing now this. Okay, if we subtract s from here and here, and so we have these two inequalities. But this means here that an minus s is in between minus epsilon and epsilon. So, and this is equivalent to saying that a sub n minus s is less than epsilon in absolute value. And this is exactly what we wanted to show for all. I mean, we gave ourselves, I mean, let's recap a little bit. So we gave ourselves an arbitrary epsilon greater than 0. And we found an n, a capital N, over here. Such that for all n greater than or equal to that n, a sub n was greater than s minus epsilon. But that was enough to show this last inequality, because by virtue of the supremum being an upper bound, a sub n will be less than s plus epsilon. So therefore we actually arrive at the conclusion. And here we don't have an actual construction of the limit, but we know that the limit exists. Okay, so that's for the monotone convergence theorem. Again, keep in mind that we want to apply all these things for the study of series. So we continue with the definition now, 2.4.3, which is the convergence of a series. So let of a series, the statement is that if we have a sequence, so let Bn be a sequence on infinite series is in principle just a formal expression. Expression of the form sum from n equals 1 to infinity of Bn, meaning, I mean, if we spell it out, it's B1 plus B2 plus etc. And so it's this formal expression because we saw at the beginning of the chapter this expression may not make any sense at all. What makes sense, though, is to define the partial sums. Here the partial sums are well-defined objects. So Sm is just it's going to be defined as the sum from n equals 1 to m of b sub n. So it's the sum of all the b's, so from b1, starting from b1 up to bm. Right? Okay. So these are the partial sums. So for each m in n, we have element Sm, or as we call it, we've been calling sequences, we're using notation for sequences so far, some a sub m or a sub n. Some only the first m terms. This is always well defined because we're only adding finitely many numbers. So we'll give proper meaning to this expression here when this sequence of partial sums converges. So we say that the series equals 1 to infinity bn, the bn's converges to b if the sequence Sm converges to b. In this case, we write that this infinite sum this is a definition, of course. I mean, this thing on the left does not make any sense a priori, but now we're going to define it as the limit b. Okay, so we're defining that, so that we're giving a proper meaning to this expression here, and only when, I mean, we actually can give it a proper meaning. That is when the partial sums converge. And if the limit is b, then we call this expression here, we assign to this expression here on the left the number b, which is the limit to the partial sums. There are a couple of examples here that we'll discuss that are kind of emblematic. I'm going to start assigning a lot of reading and explorations that you're going to have to do on your own, because there are many parts here that are going to be review. I'm just going to focus on the rigorous things that you're not used to. Perhaps you did not go over when you were an undergrad students, and so now we're going to pay attention to those things. But once we do a couple of them, you can go back and revisit all these other examples from your undergrad years, and do them on your own. So I'm going to be asking a lot of this kind of stuff from you from now on. So here we consider say a sum that some of you may already know what this converges to, so b squared over 6 by squared over 6, but okay, maybe you don't know that. And so a priori we don't know how to compute it, but we can certainly show that this actually makes sense, so meaning that the partial sums converge. So Sm is equal to 1 plus 1 over 4 plus 1 over 9 up to 1 over m squared. We will show that converges. How do we do that? First, we note that since we're always adding positive number to Sm when we want to compute Sm plus 1, then this sequence here is not only non decreasing, but it's in fact strictly increasing. We're always adding new numbers. So this, I mean, if we look at the next, so we start from Sm or Sn, and we look at the next term in the sequence, we have added a positive number, very small, but a positive number. Okay, so this implies is actually strictly increasing, so it is non-decreasing. In particular, it is monotone. So by the monotone convergence theorem, we will be able to show that this sequence of partial sums converges to a limit if we are able to show that it has an upper bound. I mean, the partial sums have an upper bound. This is what we're going to do now. So Sm is the sum over, and I'm going to write it in this way, just to make something easier to write, and equals 0 to m minus 1. So when n is equal to 0, you have 1 over 1, which is the first term, and when n is equal to m minus 1, you have m squared. So this is exactly equal to Sm. So you're adding 1 over 1 squared plus 1 over 4 plus 1 up to 1 over m squared. This is Sm. Now I'm going to do a small manipulation here. So this is less than or equal to, look at what we have inside the sum. And this is actually less than or equal to, well, what we have in the bottom here is n plus 1 times n plus 1. So this is certainly smaller than n times n plus 1. Right? I mean, just a side note. 1 over n plus 1 times n plus 1 is less than or equal to, in fact, extremely less than 1 times n plus 1. If you don't believe me, just cross multiply and you'll find out that n is less than or equal to n plus 1. Okay, so this is, I mean, we're making the denominator smaller, so we're certainly making the whole fraction bigger. So since we have that, I mean, if we are able to show that this is bounded independently of m, then we'll be done. We'll be done by the monotone convergence theorem. This is equal to m minus 1 to 1 over n minus 1 over n plus 1, and that where does it come from? Well, just do the math. So 1 over n minus 1 over n plus 1 is equal to, when you cross multiply, so we have n plus 1 minus n divided by n times n plus 1. And this gives you 1 over n times n plus 1. Now, but this is a telescopic sum, so you know the terms will start canceling out, so you only the first term and the last term will survive. Here, of course, I should have then dropped the first term, so n equals, here n equals 1. Otherwise, this will not make sense. So then you have 1 over 1. Not only that it doesn't make sense, but of course you only going to be bounding the in terms of starting from 1. I mean, not the one starting um yeah, from 0. 0 you only have 1, so I just dropped to the 1 here and get 1 plus the sum plus 1 over 1 minus 1 over m. This is 2 minus 1 over m. And then, of course, I mean, this is a negative number, so we're subtracting something from 2, so this is always less than or equal to 2. In fact, this is strictly less than 2, but later on we're going to be taking limits, so we better get used to using the less than or equal to. Even if we have a very small number and we're subtracting something, it's better to use this symbol instead of just less than. So to avoid confusion, because sometimes you want to take limits on all sides and you forget that when you take limits you have to include the possibility that in the limit the two things are equal to each other. Small piece of advice. So Sm then is less than or equal to 2. This 2 here doesn't depend on m, so no matter what m is equal to, then Sm is going to be less than or equal to 2. So 2 is an upper bound. So we can assure then since Sm is increasing, so it's monotone and it's bounded, can say, well, we can certainly say or guarantee that Sm will be convergent by virtue of the monotone convergence theorem. So we can, let me just rephrase this, so we conclude converges and this is just thanks to the monotone convergence theorem. Again, this is just this just follows from the fact that Sm is monotone and that we found an upper bound. Remember that all we need is an upper bound, right? When Sm is increasing or non-decreasing. This is exactly what we did right now. So what I'm gonna give as homework, something that you should do on your own, is example 2.4.5, which is the harmonic series, and so this is just to understand why this sequence is divergent. And this actually introduces something that we're going to see next, which is the Cauchy condensation test, which is a test that actually works when you have monotone sequences. So for the most part, it's going to be applicable, and and the terms have to be positive as well. This is actually akin to a change of variables. If you remember the integral test from Calc 1, so you may change variables, change say x by 2 to the x, say. So let me just comment on that a little bit. I mean, this is not part of the material, but remember, so if you want to add, say, sum from 1 over, say, n, just n equals 1 to infinity. Well, this is the example, the harmonic series that you're meant to show that this is divergent. This converges if and only if the integral 1 over x from x equals 1, so from 1 to infinity is defined. Well, we know that by virtue of the previous example, this doesn't, and this does not either. I mean, this does not either. One way to see that is, I mean, we can use change of variables, where x, say, is equal to 2 to the y, say, 2 to the y, and this means then that the dx dy is log, or natural log of 2 times 2 to the y, meaning I can move this thing. Dx is natural log of 2 times 2y dy. So except for a factor of natural log of 2 here, this transforms into the integral of 1 over 2 to the y times 2 to the y dy. And when x is equal to 1, y is equal to 0, so to infinity. But these two things cancel out, so you get the integral of 1. Of course, if you integrate 1 from 1 to infinity, then that is certainly not bounded. Okay, so this change of variables is actually very useful. So in fact, in the same way, we can prove that then 1 over x squared is it converges from, I mean, if you integrate it from 1 to infinity. And so that's the whole point of the Cauchy compensation test. It's a sort of a discretized version of this. Okay, so nothing really deep. I mean, it looks kind of strange when you first look at it, but if you think about it this way, then it makes sense. This is what we're going to start doing next week. Okay, so and I forgot. So this example 2.4.5 is going to be left as a homework. Nothing that you have to turn in. So you don't have to turn in this thing. You just have to cover it. I mean, look at it on your own. Look at that example. And we're going to continue next time.